So, also, I'd rather do friends than try to get them in the community. I think we got literally, yeah, literally,
It's like one of the only things that I would be worried about is like the registration or like technical processes, which shouldn't matter though.
it's like May something.
That's April that.
Oh, yeah, mine's even that.
I was like,
Okay, let's get started. So we have a lot to cover. People in the back, can you hear me? Okay, great. So last Friday we kind of gave a very brief introduction about absorption and stripping, and we talk about different types of we talk about kind of the first of all the purpose of absorption and stripping, and secondly, what's its applications, and what type of equipment, right? What type of towers we use to do this separation process, and we talk about for tree towers, the different type of trees, and the different type of like flow regimes that will affect the performance of a tree tower. We also talk about pack tower, and we talk about two types of pack tower: the unstructured pack tower and structured pack tower. And we briefly just discussed their relative advantages and disadvantages. Okay, so today we're gonna focus on tree tower. So we will basically, with some assumptions, we will introduce a graphical method in which we can analyze a tree tower, right? So if we were given a task, to kind of just to absorb a solid from a gas feed using a liquid absorbate, right? If we were asked to design a absorption tower, then how do we do that? That's kind of the question we're going to answer today. So again, before we dive into details, let's briefly review this example we discussed, on last week's lecture. So in this case, we have and this is an absorption tower, tree tower, right? With 30 trees, and we have two feeds, right? We have a feed gas coming from the bottom of the tower, going upward, and we have a liquid feed, right? That's an absorbent. That's an absorbent coming from the top of the tower and then coming down, right? We have two exit streams. We have one exit liquid and one exit gas, right? So the feed is made of, it's basically a mixture of air plus water and acetone vapor. And the acetone vapor is the chemical we want to absorb and recover by this process. So we use water, pure water, as the liquid absorbent, right? So when we feed the gas into the tower and the water into the tower, they will mix basically in each of these trees gradually as water flows down and the gas goes up, and eventually in the exit liquid stream, there will be a lot of acetone dissolved into the water, right? Basically, we kind of recover over 97% of acetone from this feed gas into the liquid absorbent water, and we only leave less than 3% of acetone, the solid, into the exit gas phase. So now we try to conceptualize that process. So in the absorber, right, we have n trees, and we number them from top to bottom, because that's where we have the top is where we have the liquid absorbents coming in. We have two phase, right? And we describe the compositions of the phase using the mole ratio, X and Y. And we have two axes, and we also use mole fraction Y and X to describe their composition. Okay. Similarly, for stripper, right? It's we have two phase here, and we have two axes, right? So stripper is like the reverse process of absorption, and it is usually coupled with absorption to regenerate the absorbent, right? In this case, for example, let's just use the acetone case as an example. If this is absorber to extract acetone from the gas mixture, then we will have a liquid stream here that's enriched with acetone, and we have a gas phase here that's depleted with acetone. Now in the stripper, the goal is to just regenerate the liquid absorbents, right? In this case, water, and by removing the acetone from the water solution, right? So we fade basically kind of think of this, you connect there, right? Connect it there. Then we fade a liquid stream that's rich in acetone into the tower from the top, and we fade a gas, right? Could still be air that has no acetone into this tower, and they were going to mix. When the two streams coming out, we're going to have a liquid stream that's depleted with acetone, because now acetone has been transferred to the gas phase and exiting from the tower in the gas phase as acetone vapor, right? That's how you regenerate the absorbers. So we use the L prime and V prime, and that's the flow rate, solute-free flow rate, right? To describe the flow rate for the for two phase and two exit streams. And the reason we do that is if we assume in the whole mixing process, right, only the solute is transferred from the gas stream into the liquid stream, and the gas stream does not condense and the liquid stream does not vaporize, then the solute-free flow rate for the liquid phase and the vapor phase will stay the same, right? So basically we have a constant L prime from the top of the tower all the way to the bottom, and we have a constant V prime from the bottom of the tower all the way to the top. Right? So that will, as I will show you in the next slide, that will greatly simplify the analysis. Okay, so again, here we use lowercase x, y to describe the mole fractions of the solute in the liquid, that's for x, and the gas phase, that's y. That's commonly used in all of our previous analysis. But here we use mole ratios instead of mole fractions. And the mole ratios are basically dependent on the mole fractions by this equation. So mole ratios of solute to the solute-free liquid is just the in the liquid stream, the mole fraction of the solid divided by the mole fraction of the solvent, right, which is 1 minus x for a binary mixture. And the same here goes to y. Okay. And the molar flow rate of the solute-free liquid can be computed by basically multiplying 1 minus x is the mole fraction of the solid. So then 1 minus x is basically the mole fraction of the solvent, right? Then 1 minus x multiplied by L. L is the total flow rate. That gives you the flow rate of your solvent, right? Solute-free solvent. Okay. And we discussed in this case, XL prime just represents the molar flow rate of your solute in the liquid phase, right? Because here, if you multiply capital X with L prime, right? Then 1 minus x here will cancel the 1 minus x here. Then you have x multiplied by L. That's the molar flow rate of your solute in the liquid stream. Same goes Y V prime. That's your molar flow rate of your solid in your vapor phase. Okay. So in the whole process for absorber, the goal is to make basically mix the gas phase that is reached in your solid with a liquid absorbance that is initially depleted in your solid. Okay, and the whole separation process will work to its maximum potential if we have really good mixing, right, between your liquid absorbance and your gas phase, right? Because in that case, if you have a good mixing, then the solid will have the maximum chance to be transferred from the gas phase into the liquid absorbance, right? And typically you achieve that, if you have very good contact between your liquid stream and gas stream, okay, and with sufficient residence time, right? If they have sufficient time to mix, okay. So in other words, when they have sufficient good mixing, we can assume that after they mix, they reach equilibrium, right? And that's actually the best absorbing tower we can design, right? If after the mix they reach equilibrium, that's when we reach the best separation effect, right? So now we're going to start from that. By assuming equilibrium at each stage, right? Remember that we have many trees, and each tree is a stage, and the downcoming liquid absorbance will mix with the upcoming vapor in each tree, right? And if we assume equilibrium at each stage, that means we assume the mix very well in that tree. Then that's kind of the case we can achieve the best separation process. So we will start from, because this is conceptually the easiest case. We will first analyze this case, and then later we'll discuss how we can connect this idealized picture with a real picture. Okay, by assuming equilibrium, the perks of assuming equilibrium is that we can just ignore the mass transfer effect, right, in each plate. By assuming equilibrium, we can just apply equilibrium constraints at each tree. Okay. So some like nomenclature here. So in this tower, we have n trees, and each tree is a stage. And then for stage I, that's for the ice tree, there will be two kind of phase, right? You have a liquid phase going into this tree, and you have a vapor or gas phase going into this tree. There will be two products. You will have a vapor gas feed product leaving this tree, and meanwhile you will have a liquid product leaving this tree, right? There will be four. Remember, just like the whole tower. So here, first of all, the nomenclature. We define the composition of the streams leaving the tree, right? X and Y with the subscript I, right? Because we are at stage I. We just described the the mole ratio of the vapor leaving the stage with Yi, and the mole ratio of the liquids leaving the stage as with Xi. That's just definition, just for convenience, right? Just remember that. Then correspondingly, this is the liquid entering stage I, right? Because we are numbering all these trees from top to bottom, from small number 1 to large number. Then this will be I minus 1, right? Corresponding, this will be I plus 1. Okay. Just familiarize yourself with this nomenclature, because we're gonna use this back and forth. So make sure you remember this, so so you won't be confused later. Now, with equilibrium assumption here, the nice thing is that then the composition of the liquid vapor stream, when they leave the tree, when they leave stage I, they will be constrained by the equilibrium condition, which is, in this case, we use, because it's a vapor plus a liquid, and we can use a key value, right? For the I key value for your solid rate. And that's the mole fraction of your solvent in the vapor phase divided by your mole fraction of your solid in the liquid phase, right? And we can so we can just based on the definition, we can just replace that with this and that with this. Okay. Okay. So here so we can write it down here. So basically remember the definition of X. Sorry. Okay. A pen doesn't work, so I'm going to use it all the way. So we can start from to get that equation, we can start from the definition. So we have X I is defined as that's a mole ratio, that's defined as a mole fraction, X lowercase x, right? That's a mole fraction of your solid rate in the liquid stream, divided by the mole fraction of your solvent, that's 1 minus xi, right? So to get that, we just need to, rewrite this equation in the format as xi equals something about, uppercase xi, right? So the way you can do that is just, I just rearrange this, or you can, well, another way is you can do this 1 minus xi. That will be, so 1 minus this term will be 1 minus x. And xi plus 1 minus x. So these two will cancel, we have 1 over 1 minus x. And then take the reverse. Take the reverse. We write this first, 1 minus x equals plus I. Then your x, xi, just move this to the right, move this to the left, 1 minus. And then just put this here, then you will have this 1 plus xi minus 1. Right. So can you see this? Can you see this? Right. So basically lowercase xi is this, right? Similarly, lowercase yi is you just replacing uppercase xi with yi, right? So just plug it in here. Plug it in here, we replace lowercase xi with this term, right? That's here. Okay. Replace lowercase xy with that. You get a key value definition based on mole ratios of the solid rate instead of mole fractions of the solid rate. Okay. Now for this nomenclature, let's just look at one example. For the first stage, right? For the first stage, that's the first stage. We have two phases getting into this stage 1, and we have 2 product streams leaving this stage 1, right? What are they? Okay, based on this nomenclature, right? I mean, 2 ways you can do this. One way is just look at this, then let I equals 1, right? And you will have, x0, y1, and x1 and y2, right? So then this corresponds to basically, at the first stage, we have the liquid stream with mole fraction of X0 coming in. We have a vapor stream with composition of Y1 leaving, right? And then you have this here. Okay. So now we're going to introduce the graphical method to describe this. Remember that in the previously when we talk about vapor liquid equilibrium, right? We introduced several graphs. We can describe the system at equilibrium. One is TXY diagram. The other is XY diagram, right? In the XY diagram, basically we plot the mole fraction of your component, one component in the vapor phase with respect to the mole fraction of the same component in your liquid phase in a YX diagram, right? So similarly here, we can plot the mole ratio, right, instead of mole fraction, right? And mole ratio and mole fraction, they're connected by this way. With respect to the mole ratio in the liquid phase, right? That will similarly give you an equilibrium curve that looks like this, right? So don't look at the operation line. We will talk about this in the next slide. So on this equilibrium curve, any point represents basically a vapor composition and a liquid composition that's in equilibrium with each other, right? So in other words, in this, for any stage, because here we assume equilibrium, right? Yi is in equilibrium with Xi. So then the composition of Yi and Xi should fall onto this curve, because that's your equilibrium curve. Okay. Now let's look at mole balance, right? That's typically how we do things for a separation process. First, let's look at the whole tower as one unit, right? We look at the mole balance. We have two streams coming in, the liquid absorbance coming from the top, the vapor feed coming from the gas feed coming from the bottom, right? Both of them are carrying certain amount of solute with the composition as of X0 and Y and plus 1, right? And then we have two streams leaving the tower, right? Then if we basically concern the mole balance of the solute entering and leaving the tower, then for the solute entering the tower, that would be X0 multiplied by X prime, right? That's this. That's the solute brought in by this stream, then Yn plus 1 multiplied by V prime, right? That's the solute brought in by this stream. That should be equal to the solute flow out, right? Then Xn multiplied by L prime, that's the solute brought away from the tower by this stream, and this is the solute brought away from the tower by this stream. Okay, very simple. Recall here, always XL prime equals lowercase xl. We can also do this for a control volume. We can draw a control volume that's basically circling the stages from stage 1 to stage small n, right? You can always do that. And this n can be arbitrary, right? Because we can draw a control volume anywhere we want. And you apply the same analysis, right, for the control volume with n stages from 1 to n. Just do the same. In this and that will be the same, right? These two will be the same. What is different is here below this nth tree, your vapor coming in will be y small n plus 1, and your liquid leaving will be xn, right? Now, with that, we can derive a equation like this, right? So how we derive that? This is basically kind of not very difficult. So here, still So, so because you have L prime on both left and right hand side, you have V prime on both left and right, right? First thing we do is just to, we sum all the terms with L prime together and V prime together, right? So for example, we move x0 L prime to the right. That will give us xn minus x0 L prime, right? Then we move this term y1 to the left. That will give us y. So now if you look closely, we can divide v prime to the right, right? So we have y plus 1. Okay. Well, now you can see this is kind of a then you move y1 here to the right, you get this equation, right? So basically, what does this mean? This means, first of all, if we drop the subscript for y, right? If you drop y here, then and then you drop n here. This is basically a equation for a straight line on y versus x plot, right? Y versus x plot, you have a straight line, and this straight line goes through basically the point of goes through the point of x0 and y1. Goes through the point with a coordinate of x0 and y1 with a slope of L prime over V prime, right? So this line we call it as operating line. The reason we call it operating line is basically when you do this for different control volumes, right? You can always do this. Let n equals I. Redo this, you will find out point xi and yi plus 1 will always fall on the same line, right? And we know this. What are these? What are these? This is basically the composition of the liquid stream leaving stage I, right? And this is the composition of the gas phase entering stage I, right? So then now we have this slope of the operating line. What happens if the slope goes to infinity? Okay, so I think you know the answer here. Basically, then your operating line will be a vertical line, right? Similarly, if your this goes to 0, your operating line will be a horizontal line. So the physical meaning here is, if you have, for a given gas flow rate, if you have an infinite amount of liquid absorbance to do the absorption, your operation line will be vertical. Otherwise, in this case, your operation line will be horizontal. Okay, so again, operation line just means for a stage I, right? For any stage I, the composition of the liquid stream leaving this stage and the composition of the gas phase entering this stage, they are constrained by this equation, right? Graphically, this a point given by this coordinate xi, yi plus 1 will fall on this operating line, right? That's graphically. Now, let's look at several representative points in this figure. What does this point mean? Any? What does this point, right? This point, red point, at the bottom of this operating line, what does this point mean?
Conditions of your your top inlet and then your top outlets.
Yes. What does this point mean? The orange.
Bottom.
Yes. Yeah. So these 2 points, right? Once, if for a tower, if we specify the fit composition x0, yn plus 1, if we specify the product composition y1 plus and xn, right? They then basically this give us 1 point on the operation line. That's your basically this line here, top line here, right? This x0 and y1 defines the basically the bottom line on your operating line. Okay. So then you have this operating line defined, right? Now, reason x0, y1 is on the left or is lower than that is basically for an absorber. As your liquid absorbance flowing down, it's gonna gradually picking up the soil rate, right? So the value of x will increase. So which means xn is always larger than x0. Right? That's why on this figure, xn is on the right side of x0. Similarly, for this gas stream, when it enters this absorber, as it goes up, the solute in this gas stream will be transferred into the liquid stream, right? So y will decrease. So yn plus 1 will be larger than y1. That's why this point yn plus 1 is higher than y1. So now, if we just pick a random point on this line, let's say if the coordinate of that line at that point is x1, xi and yi plus 1, what does this point mean?
Right.
Yes. So here, basically, we're looking at ice tree, right? Stage I. That point gave us the composition of the liquid stream leaving and the gas stream entering the stage I. Okay. Now, what if we from this point we draw a vertical line, right? This vertical line will cross the equilibrium curve at this orange point, right? What does this orange point mean?
What's leaving the tray?
Yes. So this orange point means basically if you draw a vertical line here, this point will have the same x coordinate at this point, right? So this point will have the same x coordinate. So the x coordinate will be xi, same as that. Now we talk about this is the equilibrium curve, and based on equilibrium assumption, xi is here, right? Based on equilibrium assumption, we know that the liquid stream leaving the tree is in equilibrium with the vapor stream leaving the tree, right? Then the y coordinate of this point basically gives you the composition of this, gas phase leaving the tree, right? Now, if we draw a horizontal line here, and that horizontal line will again cross this equilibrium curve, what does this point mean?
Going into the tray.
Yeah. So again, when you draw a horizontal line, right? That means this point will have the same y coordinate as this point, which is 1i plus 1, right? And we know here 1i plus 1 is the composition of the gas phase entering stage I, right? And because we know this point corresponds to an equilibrium, and that means the x of this point, that's x I plus 1, corresponds to the composition of the liquid stream leaving the tree below it, right? So this takes some time to digest, but I have the definitions left here. So just it takes some time to just really be proficient at this. But go back and spend some time thinking about it, and it's not difficult. Just remember, right? At any point on the equilibrium curve corresponds to in our system corresponds to a composition leaving a certain stage I, right? Because that's our definition. We define with the equilibrium assumption, we define any stream leaving a stage I, right? The liquid stream and the vapor stream, they will be in equilibrium. So their composition is constrained by the equilibrium curve, right? And any line on this operating line means that's basically the composition below or above any stage, right? Based on mass conservation derivation, the composition below a stage I or above the stage I, they are constrained by the linear function we just derived, right? So they should fall on this operating line. Okay. Then if you draw a vertical line, on this vertical line, all the points will have the same x coordinate. Yes.
So I'm just kind of curious, we're trying to get the lowest concentration of solute, right? That's the goal of the tower, to absorb the solute out.
Yeah, yes, in the exceeding gas phase. That's a goal.
So you want Y to be minimized then? Is that what you're saying?
Y want to be minimized. Right? But typically that's not the design goal. The design goal is you specify a Y1, right? So you basically ask to design, hey, design an absorption tower, right? Start from a Y1 of 20%, but with start from a Yn plus 1 of 20%. That's your gas phase composition. Make sure when the gas phase leave the tower, its composition drops below 1%, right? That's Y1 equals 1%, right? Then how do you design this absorption tower? What are the flow rates for your liquid absorb rates, right? Given a fixed vapor flow rate, what are the flow rate of your liquid absorb rates coming down? How many stages do you need to achieve that? That's what we're going to answer, after we understand because we're going to do that graphically. But before we can do that graphically, we have to understand what does the graph mean, right? We have this graph, we have two lines. What does these two lines mean? Right? What does these two lines mean? What does every point on these two? Okay, so any point on vertical line will have the same x coordinate. Any point on vertical horizontal line will have the same y coordinate, right? So just remember that, and then you should be able to figure this out. So now, with that said, that means now for any stage I, right, we have two incoming streams, right? In this case, xi minus 1 and yi plus 1. They are entering this stage I. Then we have two exceeding streams, right? Xi and yi. Once the operating line and equilibrium curve is defined, then given any of them, I can find out the rest three of them, right? So let's just look at one example, right? Let's say if we know for this stage I, if we know the composition of the entering gas phase, right? That's one, y, I plus one. How do we find the other three? Right, let's see if y, I plus one here. First, let's draw a, first of all, we know these two compositions are constrained by the operating line, right? The first thing we do is to, from this y, I plus one, we can look for xi by looking at operating line, right? What you do is just draw a vertical, horizontal line here from y, I plus one, that will cross the operating line. Then the x coordinate of that operating line is xi, that gives you that, right? That's the first step. Second step is, now we know this is in equilibrium with that, right? This xi is in equilibrium with xi. So to find out, once we know this, we can find out the composition here. You just need to go to the equilibrium curve, right? So we draw the way you graphically you can do that is you draw a vertical line, right? From this point, that vertical line will cross the equilibrium curve at this point, right? And then that point, the y coordinate of that point is yi, right? Now we have yi, okay? Again, we know these two compositions are constrained by the operating line, right? You just need to graphically, we just need to, draw a horizontal line, and this will cross the operating line at one point. And the x coordinate of that point, x1 minus 1, give you the composition here, right? So mathematically, what I just showed you, is graphically, mathematically, what does this mean? Mathematically, that means we have 4 variables here, right? Now, we're applying the degrees of freedom analysis we are familiar with. There are 4 variables here, right? And these two are in equilibrium, so there's one equilibrium constraint equation we can write down. These two, they are constrained by the operating line, so there are 2 more equations we can write down based on the operating line equation, right? So we have 4 variables, we have 3 equations, so the degrees of freedom is 1. That's why as long as we specify, any of these 4 compositions, that the rest 3 are defined, okay? And we're going to use this kind of, rule later to, yes.
I'm a little bit confused about what top and bottom on the operating line mean. The dot for yi, xi minus 1 is off of our operating line. Does that mean it's impossible for the system that we have, or it's impossible for the tray that we have?
Can you rephrase your question?
The last purple dot that you drew is outside of the bounds of our operating line.
Mm-hmm.
So does that mean that it's impossible? And is it only for the tray, or is it for the entire process, like the entire tower?
Yeah, so that's a good question. So first of all, this is your starting composition. I mean, not starting composition. That's your top composition at your top of your tower, right? And if your real operation line is like this, you cannot have this point there. Right? But here, this example is just to show you graphically what does this mean, right? So you can just think of this line is stretching out. This is just one example. Right. So okay, let me put it this way. In this example, let's assume you have an operating line stretched all the way through, right? So you don't have to worry about the physical meaning of these 2 points. Right. B, if there's really a operating line that looks like this, when you do this stepping process, you will find out a point outside this line. That means you cannot achieve that. Right? Does that make sense?
Also, this example, that would be a one tray tower then. If our operating line does look like that would be like one tray to accomplish all of
Yeah.
the process.
Yes. Yeah. We'll talk about number of trays or number of equilibrium stages later, right? But this is just to prep you to familiarize yourself with the meaning of the equilibrium curve and the meaning of the operating line, and what does it mean when we draw a vertical line here, what does it mean if we draw a horizontal lines here? Because that's the graphical, that's the basis for the graphical method we're gonna apply later to find out how many stages we need to achieve the desired, design goals. So from this, what we can get is for absorbers, the operating line is above the equilibrium line, right? So operating line is above the equilibrium curve for absorber. For stripper, the operating line lies below the equilibrium curve, right? Why? The reason is this, right? So just look at, for example, let's say if we compare this point with this point, right? They have the same x coordinate. They have different x y coordinate, right? So this point is here. This point is here, right? So this point tells us the composition of the gas stream entering the stage I. This point tells us the composition, the y coordinate tells us the composition of the gas phase leaving the stage I, right? And we know that yi for an absorber, yi is smaller than yi plus 1, right? Because as the vapor goes up, part of the solute in the vapor phase is in the gas phase is transferred into the liquid phase, right? So yi is smaller than yi plus 1, right? That's why equilibrium curve sits below your operating line, right? Does that make sense? Right. For absorber, then it's the other way around. So now let's just look at some examples. We can now we have the operating line, right? Let's just look at some examples how operating line is helpful for us to analyze the absorption problem. So this is the equation for the absorption line. This is our absorption tower. So let's say if we know the phase stream compositions, right? We know x0, we know yn plus 1, those they are the feed. We know the gas flow rate, right? Which we know V prime. We know xn and y1. Let's find out the solvent flow rate, right? Let's find out L prime. How do we do that? Graphically, so just put all the known information on the figure, then the answer will basically be obvious. So here we know feed composition, so and the y1 xn, right? So which means when we draw the operating line, we have this point given, right? X0, y1. You find a 1 point, then we have the other point given, xn, yn plus 1. You get that point. Then you can draw a line. The slope of this line can be measured, right? Then we know v, right? Then we know L prime over V prime is a slope, right? Then L prime is just V prime multiplied by the slope. Okay. That means, in this case, we have, these variables here. As long as you know this, you can figure out the solvent flow rate by, plotting the operation line. Okay. We'll look at some other examples Wednesday. Let's stop here.
That sounds like someone's going to that's not what we can do right now. Walking in the rain, but over that it's snowing in some places. I know it's a little less. But I'm not either.